In physics, a surface wave is a mechanical wave that propagates along the interface between differing media, usually as a gravity wave between two fluids with different densities. A surface wave can also be an elastic wave, such as with a Rayleigh or Love wave. It can also be an electromagnetic wave guided by a refractive index gradient. In radio transmission, a ground wave is a surface wave that propagates close to the surface of the Earth. Mechanical waves. In seismology, several types of surface waves are encountered. Surface waves, in this mechanical sense, are commonly known as either Love waves or Rayleigh waves. A seismic wave is a wave that travels through the Earth, often as the result of an earthquake or explosion. Love waves have transverse motion, whereas Rayleigh waves have both longitudinal and transverse motion. Seismic waves are studied by seismologists and measured by a seismograph or seismometer. Surface waves span a wide frequency range, and the period of waves that are most damaging is usually 10 seconds or longer. Surface waves can travel around the globe many times from the largest earthquakes. Surface waves are caused when P waves and S waves come to the surface. The term surface wave can describe waves over an ocean, even when they are approximated by airy functions and are more properly called creeping waves. Examples are the waves at the surface of water and air, or ripples in the sand at the interface with water or air. Another example is internal waves, which can be transmitted along the interface of two water masses of different densities. Electromagnetic waves. Ground waves refer to propagation of radio waves parallel to and adjacent to the surface of the Earth, following the curvature of the Earth. These surface waves are also known loosely as the Norton surface wave, the Zerneck surface wave, Sommerfeld waves, and gliding waves. See also Diakonov surface waves propagating at the interface of transparent materials with different symmetry. Radio propagation. Lower frequencies, below 3 MHz, travel efficiently as ground waves. This is because they are more strongly diffracted around obstacles due to their long wavelengths, allowing them to follow the Earth's curvature. The Earth has one refractive index and the atmosphere has another, thus constituting an interface that supports the surface wave transmission. Ground waves propagate in vertical polarization, with their magnetic field horizontal and electric field vertical. At VLF, the ionosphere and Earth's surface act as a waveguide. Conductivity of the surface affects the propagation of ground waves, with more conductive surfaces such as seawater providing better propagation. Increasing the conductivity in a surface results in less dissipation. The refractive indices are subject to spatial and temporal changes. Since the ground is not a perfect electrical conductor, ground waves are attenuated as they follow the Earth's surface. The wavefronts initially are vertical, but the ground, acting as a lossy dielectric, causes the wave to tilt forward as it travels. This directs some of the energy into the Earth where it is dissipated, so that the signal decreases exponentially. Most long-distance, low-frequency, long-wave radio communication is a result of ground wave propagation. Medium-wave radio transmissions, including in broadcast band, travel both as ground waves and, for longer distances at night, as sky waves. Ground losses become lower at lower frequencies, greatly increasing the coverage of AM stations using the lower end of the band. The VLF and LF frequencies are mostly used for military communications, especially with ships and submarines. The lower the frequency, the better the waves penetrate seawater. Even extremely low frequency waves have been used to communicate with deeply submerged submarines. Surface waves have been used in over-the-horizon radar, which operates mainly at frequencies between 2 and 20 MHz over the sea, which has a sufficiently high conductivity to convey the surface waves to and from a reasonable distance. In the development of radio, surface waves were used extensively. Early, commercial and professional radio services relied exclusively on long-wave, low frequencies and ground wave propagation. To prevent interference with these services, amateur and experimental transmitters were restricted to the higher frequencies, felt to be useless since their ground wave range was limited. Upon discovery of the other propagation modes possible at medium wave and short wave frequencies, the advantages of HF for commercial and military purposes became apparent. Amateur experimentation was then confined only to authorized frequencies in the range. Medium wave and short wave reflect off the ionosphere at night, which is known as skywave. During daylight hours, the lower D layer of the ionosphere forms and absorbs lower frequency energy. This prevents skywave propagation from being very effective on medium wave frequencies in daylight hours. At night, when the D layer dissipates, medium wave transmissions travel better by skywave. Ground waves do not include ionospheric and tropospheric waves. The propagation of sound waves through the ground, taking advantage of the Earth's ability to more efficiently transmit low frequency, is known as audio. Ground wave. Microwave field theory. Within microwave field theory, the interface of a dielectric and conductor supports surface wave transmission. Surface waves have been studied as part of transmission lines, and some may be considered as single-wire transmission lines. Characteristics and utilizations of the electrical surface wave phenomenon include: the field components of the wave diminish with distance from the interface. Electromagnetic energy is not converted from the surface wave field to another form of energy such that the wave does not transmit power normal to the interface, i.e., it is evanescent along that dimension. In optical fiber transmission, evanescent waves are surface waves. In coaxial cable, in addition to the TEM mode, there also exists a transverse magnetic mode which propagates as a surface wave in the region around the central conductor. For coax of common impedance, this mode is effectively suppressed, but in high impedance coax and on a single central conductor without any outer shield, low attenuation and very broadband propagation is supported. Transmission line operation in this mode is called E-line.